Okay, good morning, welcome back. Today we'll see some more vignettes from social choice. Okay. And so what I'm going to do is I'm going to explain I'm going to just introduce a couple of concepts at the beginning. Okay. And not in great formalism, but just so that you're familiar with those concepts. And then I'm going to give 3 examples of how these concepts are used in sort of somewhat in practice, but also somewhat conceptually. Okay. So the first concept I want to study is I want to describe several voting rules. So we talked about Arrow's impossibility theorem last time, and we said that there is no voting rule which satisfies all 3 criteria. We also discussed Gilbert-Satterwade, but we haven't really looked at specific voting rules. And while those are not super relevant to what I'm going to talk about today, I feel like any tutorial on social choice would be incomplete without some mention of voting rules. So to explain voting rules, I'm going to again assume that I'm given n voters. I'm going to assume we are given m alternatives. I'm going to assume that each voter gives a ranking. Okay. I'm going to for now assume it's a complete ranking, but pretty much everything I'm going to say works with ties. Gives a ranking of all candidates. Okay. And these rankings, we can think of these rankings as a permutation sigma I. Okay. So sigma ij is the position of the jth candidate in the ith ranking. Okay. So what are some of the most commonly used rules? So the one more rule which is used most commonly is plurality. Okay. And plurality says that the winner belongs to the in the ith ranking, yes. Okay. So plurality says that the winner must be somebody So repeatedly throw away a candidate in which gets the least first place votes. When you're left with only one person, you declare that person as the winner. And single transferable vote or rank choice voting is also amenable to choosing many winners. So you keep throwing people away. If you want to choose k winners when you're left with k people, that's your rank choice voting. Okay. Then a third one, which is commonly used, is Borda. Okay. And so what happens with Borda is that so I'm going to define Borda in two ways. In one way because it's easier to understand, in the other way because it's going to be lead to what I'm going to talk about next. Okay? So in Borda you define a score of J as the sum over all I of m minus sigma I j. Okay? So in each ranking, you give the first guy a score of m minus 1, the second guy a score of m minus 2, the third guy a score of m minus 3, the fourth guy a score of m minus 4, all the way down to 0. Okay? So, and then the person with the highest score wins. And another way of defining the same score is that the score of j is the sum over all j prime not equal to j. So you look at every other candidate other than j of the number of rankings in which j beats j prime. Does that make sense? And so because it's m minus sigma I j, this is exactly equal to the number of guys I beat. This is exactly the number of candidates that j beats in I, and I interchange the order of summation. Instead of I sum over all j. Okay? Now the reason I club these three together is that pretty much every election that runs, as far as I know, uses one of these three. Okay? You also have like instant runoff, which is sort of like single transferable vote, okay? Just applied with revoting. But all three of them serve from like a pretty fatal flaw, which I'm going to point out next. Okay? Can someone sort of point out? So if you were to think of these, if you were to go a little bit beyond Arrow's impossibility theorem, right? Arrow's impossibility theorem is very general, applies to everything. If you wanted to say, well, if my rankings have a certain property, then I want a certain outcome. Okay? So what we did for Gibberts-Satterthwaite is that we said, if our utility function has a certain form, then we can get a certain incentive compatible result, right? So for Arrow's impossibility theorem, what we would like to say is if our rankings have a certain form, we're going to get a certain kind of guarantee. Okay? So can someone think of like some properties that you could impose on rankings and say if our rankings have this form, then we want this outcome? As opposed to looking at all rankings, where Arrow's impossibility theorem essentially says that we can't really do much. Yeah. See, so you're looking at some kind of a turnover. So you could assume that these rankings are coming from a pairwise from a peaked preference model. Yeah, that's very nice. So you could assume that all the candidates that you have are coming from a pairwise from a distance model. Okay? So you could say that the candidates are points on a line Okay, so these are candidates. You could assume that the voters are also points on a line. That a voter's ranking is determined by how far the candidate is from the voter. Right? Well, I mean, why a line? You could say that, well, a voter's ranking depends on how far you are in any metric space. Does that make sense? You could say that these people, that you could assume that voters and candidates lie in some metric space, or to begin with, let's say some high dimensional geometric space, but in general some metric space. And you could say a voter's ranking of all the candidates depends on the distance in this metric space. Okay? So you could totally do that. So that's one very reasonable assumption. And in fact, that's something that we're going to see. You're going to see under the assumption that these voters and candidates comes on some metric space, some specific kind of metric space. Yesterday we saw an example of a line. Today we might see something a little bit more general. What can you do? Okay? Is there anything else that you could imagine saying about the rankings? So let's look at one example, and let's see if we can determine for this example who the winner should be. Okay? So let's look at the example of let's say this is ranking 1. Let's say ranking 2 is B, A, C, and let's say ranking 3 is C, let's say B, C, A, and let's say ranking C, ranking 3 is C, A, B. In this, is it clear who the winner should be? No, right? It's not clear who the winner should be. But suppose I make it BAC. A should be the winner. Yeah. Yeah. So it seems like in this case, it seems like A should always win. And so one argument could be that if you look from top to bottom, then A has they both have equal first place votes, but A has more second place votes. That reasoning itself, in this example, it works. In general, it might lead us to a problem, because that would be too similar to ranked choice voting. And also, you could imagine that some funkiness is happening down here. So, yeah. Yeah. So I think in general, errors impossibility theorem says, so the question is, well, how can you generally do it? You can't do it in general. Okay? So I think what you outlined is one reasonable way of looking at it. There's a little bit of an artifact of the fact that you have only 3 candidates. The fact that you can use the second place to determine the winner, because there's too much like plurality. So another way of thinking of this is that let's just focus on A and B. Okay? A beats B here, B beats A here, and A beats B there. So if you have to take a projection of this election down to just A and B, and project these rankings down to just A and B, it looks like we have AB, BA, and AB. So A beats B twice. Okay? A also beats C twice. Okay? So A would win a pairwise election against B, and A would win a pairwise election against C. Does it make sense? If you were to project these, so is it clear what I mean by projection of a ranking down to a pair? You just ignore everybody else, just look at the pair. Okay? So in this particular case, A beats everyone else in a pairwise election. Okay. And this implies that A is a Condorcet. This not implies, this is a definition. So this, a candidate who beats everyone else in a pairwise election is called a Condorcet winner. Okay. Does this make sense? Yeah. So in general, we would like to have this property that when there is a Condorcet winner, the Condorcet winner should win. Okay? And so it's a very non-controversial property that when there's a Condorcet winner, you should have the Condorcet winner should win. Yeah. No, all 3 orders. So there are 3 rankings. So if I just limit myself to A, if I project it down to A and B, the rankings look like A, B, B, A, B. So in a pairwise election, A gets 2 votes, B gets 1 vote, so A wins. Yeah. So basically you can say the A beats B if the set of I where sigma I A is as in sigma I B is more than n over 2. Okay. And so this seems like a really non-controversial rule, and is well connected with the one argument that Rajesh made, which is that on a line, it should be somehow if you can assume that the ranking comes from a line, you should be able to do something nice. And the reason it's connected is when the ranking comes from a line, there's always a Condorcet winner. So you can show that if candidates and voters come from the line, then there's always going to be a Condorcet winner. So this criterion is a little bit more general than saying that everyone is from a line. Yeah? So let's also see C. Yeah? So in terms of C, A beats C in the first one, A beats C in the second one, and C beats A in the third one. So the score of A against C is also 2:1. Yeah. So A is the Condorcet winner. Thank you. So you have to verify. So to make sure that someone is a Condorcet winner, you have to go and check against all 3. Okay? And now, as I said, these are the only 3 rules that I know anyone ever uses in any significant elections, and none of these is a Condorcet rule. And a Condorcet rule is a rule which says that if there's a Condorcet winner, then you have to find a Condorcet winner. So a rule is said to be a Condorcet rule if the winner that it outputs is a Condorcet winner if one exists. So a Condorcet winner need not always exist. But in my mind, any sane rule should output a Condorcet winner when one exists, because such a non-controversial quantity. And none of these rules output a Condorcet winner. No, C, in this case, no, C doesn't win because if we just project the ranking down to A and C, it becomes AC, AC, CA. So C is losing against A, so C is not a Condorcet winner. Depending on how you define a Condorcet winner, if you allow ties, you can sometimes have multiple Condorcet winners. But that's sort of a technicality and doesn't really matter either way. In this particular example, there's definitely a clear Condorcet winner, which is A. Yeah. And then, yeah? Yeah, I mean, they could. I don't know why they don't, because the rules which are, I think one of the reasons that they don't is because a Condorcet rule really does require people to give you a complete ranking. No, none of these is a Condorcet rule. So there exists examples, for each of them there exists an example where there's a Condorcet winner, but this rule will not find one. Yeah. So in fact, maybe I'll give you an example very soon, yes. No. No. So it's not true, because in fact, we just saw an example where there was a cycle, and if you ask for a strict Condorcet winner, then none existed. If you define a Condorcet winner by saying you have to beat someone 2:1, then even otherwise there was no Condorcet winner. Because when I had ABC, BCA, and CAB, then A beats B, B beats C, and C beats A. Yeah, so I think, so what you're saying is that you should actually look at how much difference there is. So you're assuming that if I am ranked, so you're saying that a difference between 10 and 12 is not the same as the difference between 10 and 1. Yeah, so it's possible. So maybe a Condorcet rule, so I guess that's also a valid point of view, that maybe I shouldn't say that a Condorcet winner when it exists is a reasonable thing to do. But among all the criteria that I know of, so again, because of Arrow's impossibility theorem, nothing is going to be fully satisfactory. among all the criteria that I know of, just saying that if there's a Condorcet winner, you should choose a Condorcet winner, is the one that seems the least controversial. I mean, of course, you could normatively say that you want Borda. But, I mean, there's no, you could say it, but there really is no normative or axiomatic support for saying why Borda is a good thing. Whereas for Condorcet, I can at least say that I'm choosing this winner because it beats everybody else. Right? And so, so in particular, if you choose anyone else, the Condorcet winner can come and complain, I beat that guy. Yeah. I mean, that's basically the US primary last year, a couple of years ago, right? The people who might have claimed that they could have beaten Trump one-on-one, but they didn't win. So I'm going to give you an example where plurality is not Condorcet. It's going to be very simple, and once you see that, you'll be able to see why single transferable vote is also not Condorcet, because the examples are very similar. Okay. And then I'm going to give you a couple of Condorcet rules, and then I'm going to move on to sort of the next thing that I want to give as a primer before I go to actual research ideas. Yeah. No, I've not seen any crisp characterization of existence of Condorcet winners. There are specific cases. For example, if preferences come from a line, then there's always a Condorcet winner. Yeah. But there's not really. In fact, you look at the median voter, and whoever is closest to the median voter is going to end up being a Condorcet winner. Yeah.
So does it mean that whenever there is no Condorcet winner, you always have a cyclic combination of beating?
Yeah, whenever you don't have a Condorcet winner, there'll always be at least one cycle. Because otherwise you can imagine defining a directed graph where you run edge from A to B if A beats B, or if B beats A, and you keep following it. If you get to a sink, then you found your Condorcet winner. Yeah. So you'll always be, so the two are equivalent. Yeah. Yeah. So I guess you could think of that as a characterization, that in the tournament graph there's no sink. But there's just like a structural characterization in the sense that that just follows from the definition. It's not something which is sort of going deeper into the rankings. Okay. So let's see an example of why plurality does not have a Condorcet winner. And so let's look at the case where the rankings are A. Okay. Rankings are A, B, C, D. Okay. And I think this example came from somewhere about like gold and silvers. Okay. And then it doesn't really matter how things are arranged at the bottom. E is going to beat everybody. Because E is going to beat, regardless of where A occurs here, E is going to beat A 3 times. It's going to beat B, C, and D 4 times. And it's going to be beaten by only twice. Okay. So E is a Condorcet winner, but plurality will clearly find A. Single transferable vote will also clearly find A, because E will get kicked out right away, because it doesn't have any first place votes. And then B, C, and D will get kicked out subsequently. Borda, you can prove that Borda, in fact, any position scoring rule, any rule that assigns a fixed weight to every position. So Borda was a position scoring rule because you were assigning a weight of m-1 to the first position, m-2 to the second position, and so on. Any position scoring rule is not a Condorcet rule. Okay. So what kind of rules could be Condorcet rules? So one kind of rule that could be a Condorcet rule is just something which is explicitly designed to be like a Condorcet rule, and so the simplest such rule is Copeland. So Copeland is this rule where you assign a score of J is J prime So score of j is the number of other candidates j prime such that j beats j prime in a pairwise election. Okay. Now, if there is a Condorcet winner, there is going to be someone with a score of m minus 1. If there is no Condorcet winner, nobody will have a score of m minus 1, but you could pick the one with the highest score. Okay. And so the Copeland rule says, I am going to call it the Copeland score just to distinguish it. Okay. Pick the candidate with highest Copeland score. Okay. And so this rule, because when there is a Condorcet winner, will have a score of m minus 1, and so you could say, well, let's pick the candidate with the highest Copeland score. Okay. Then another rule which is, there are sort of many variants which sort of look like Copeland, and I don't want to get deep into sort of variants which are too much like Copeland, so I want to give you another variant, another thing which is very different from Copeland, okay. And that's called rank pairs. So the question is, this seems too tailored towards whether there is a Condorcet winner or not. I don't know whether, I mean, what you said was a statement, but I think what you are pointing out is an objection. And the objection seems to be that this is. Yeah, I mean anything, yeah, so you could just say, you could just first find whether Copeland Condorcet winner exists. If one exists, you do the Condorcet, otherwise do plurality. Those rules tend to be more brittle. No, I mean this is sort of more integrity in the sense that, I mean if you think that the Condorcet criterion is important, then you should do this. If it's not important, then do plurality. Somehow, like the mixture sounds a bit strange. And I have some concrete reasons why the mixture sounds a bit strange, which I'll explain in a minute. Copeland, so the Copeland is a well-defined rule. It always gives you a winner, right? So because I mean it's a score, so you always find a winner. If there's a Condorcet winner, then you find the Condorcet winner. Otherwise, you find someone else. Okay? You can use the same rule to find more and more and more. Okay. So then, the next winner is what's called, the next thing is called rank pairs. Okay. And in rank pairs, what happens is that you draw an edge from j to j prime. The weight of, you draw an edge from j to j prime. And this edge, so is just the number of, I should have just defined this before because I've been writing this again and again. Okay. It's the same quantity that we've talked about. W of j comma j prime is the number of rankings in which j beats j prime, or the number of voters who think that j is better than j prime. Okay. And so rank pair says that you arrange all voters arrange and when I say pair, I mean ordered pairs. So A comma B and B comma A are different pairs, okay, of voters in decreasing order. It's not a set j comma j prime, it's like the ordered pair j comma j prime in decreasing order of W j comma j prime. Okay. So you basically take all possible edges in this graph. So we alluded to this graph this directed graph where you draw an edge from J to J prime if JB is J prime. Imagine all possible edges in the graph and you arrange them in decreasing order of W. Okay. And then you repeatedly add these candidates, yes. Thank you. I'm going to mention it just now, yeah. Sorry, thank you. All pairs J comma J prime of candidates in decreasing order of W J comma J prime. And then you repeatedly, you make a graph, okay, where V is just the set of candidates. Okay. And to obtain E, and so to design E, you pick J comma J prime in order. Okay. So you pick these directed edges J comma J prime in this order in the decreasing order of W J J prime, and you add them to E if it does not cause a cycle. Does this make sense? Okay. So I'm going to pick, so basically the heaviest edge that exists is the first edge that's going to get picked. Okay. I'm going to keep adding these edges to E as long as there's no cycle. Okay. And because there's no cycle at the end, I'll be left with a DAG. And that DAG will have a source, and that source will be the rank pairs winner. Okay. So at the end, a DAG is a directed acyclic graph, so you're going to have a directed graph. There are going to be no cycles because you're not adding edges that cause cycles. But because you're biasing towards heavy edges, people who beat each other more soundly, are more likely to come out as the winner. At the end, you're going to have a DAG, and then source of this DAG. It's a DAG, and between any two nodes there's going to be at least one edge, either from J to J prime or J prime to J. And so you're going to have the source of the DAG will be the winner. Okay. In fact, it's going to give you a complete ranking. Okay, so this is rank pairs. And so rank pairs also ends up being a Condorcet consistent rule. Just because it's sort of, if there's a Condorcet winner, it's not going to be beaten by anyone. So it's never going to have any edges pointing to it. So whenever you're done with the DAG, it's of course going to be the source of the DAG. So now we have these rules. Since the source need not be a Condorcet winner, but there is a Condorcet winner, there will be the source. So the rank pairs is a very attractive rule. Because it has this property, so there's this property sort of, it doesn't quite take into account the objection that you had that 10 and 11 might not be the same as 1 and 10. But it does have this, it does take into account how much you beat someone by. Whereas Copeland doesn't really take into account how much you beat someone by, just whether you beat them. Okay. So Copeland and rank pairs are different rules. When there's a Condorcet winner, then they coincide because they'll both output the Condorcet winner. And so this brings us back to this question, given all these rules, is there some, so Condorcet winner is a nice way, so I find it to be somewhat normative, but is there some other way of distinguishing between different rules? Like is there some way you could say, well, if one rule is there some other way by which you could claim that one rule is better than the other, right? Which is a little bit less controversial, or which is a little bit more generative. So I'm going to give, I wasn't going to give it, but since that question came up, I'm going to define a way of comparing different rules, which is a little bit more from first principles. Okay. And then I'm going to sort of point out what's known and what's not known and outline an open problem. And that might mean that I wouldn't be able to cover another thing that I was going to cover, but I think this is, since we're doing it, might as well finish doing it. No, so they all give a ranking. So plurality gives a ranking. This, because it's a DAG, gives a total order. Copeland gives a ranking. Yeah. STV doesn't quite give a ranking, but you can. Yeah, because every edge is ultimately going to get added. No, sorry, every edge is ultimately going to be attempted. So if two nodes are incomparable, then you'll add the edge between them at some point. So if they're incomparable means there's no path from one to the other, which means by adding an edge there, you're not creating a cycle. So between every node, there'll be some, so this will give you what's called a tournament graph. It means that between any two pairs of nodes, there'll be an edge going in this direction or that direction. In general, tournament graphs can be cyclic because England might beat Belgium and Belgium might beat Sweden and Sweden might beat England. But because we are explicitly ruling out cycles, you get an acyclic tournament graph and it'll give you a complete ranking.
How do you decide so which weight do you start with?
The heaviest edge. So you're not ordering nodes at the beginning, you just order edges and you keep picking edges from the top. Between any two nodes, there's an edge either in this direction or in that direction. When you get to that edge, if those nodes are not comparable, then you'll add that edge. So which is why you know that at the end when you are done, every node is comparable, every pair is comparable. So they'll give a complete ranking. And this sounds like a very beautiful rule. And Copeland sounds a little bit more shaky. And plurality, STV, and BODA are the only ones that actually get used. And so it'll be good to have some way of comparing them. I haven't made slides on it. This is the kind of thing for which I would need slides to do it complete justice. I have slides somewhere in my directory, but I don't want to muddle through them now. So I won't be able to give you the full, the proof, but I at least give you the outline. Okay? And so the basic idea is similar to what you were saying before, that what if they're on a line, okay? Well, let's say a line is too simple. I don't believe a line really captures the diversity of people's beliefs. Okay? So let's assume that voters and candidates lie in a metric space. Okay. So let's assume that, so we are still in the same model. Okay. So this is going to be an additional assumption that we are making on top. We are still given rankings. We are still given M candidates. We are still given N voters. Okay. Each voter has given us a ranking. We are still faced with exactly the same problem where we are aggregating the ranking. Okay. We are making an additional assumption that there exists a metric space D x comma y okay. We give a metric space D x comma y and we are given and both voters and candidates are in this metric space. Okay. Does it make sense? Okay. And I'm going to assume that sigma I, the ranking sigma I, okay, is in increasing order of Dij. Does it make sense? Okay. So the ranking that's given to us is increasing order of Dij, okay. But we are still given rankings which we are aggregating. We're going to assume we don't actually know D. D exists. There's some metric space from which people's opinions come. Okay. But it's an arbitrary election. People are voting up against sort of should Catalonia secede from Spain? Who knows what metric space they're optimizing in? Like there's some complex historical, racial, ethnic, economic, multidimensional space in which their opinions lie. Okay? So we don't actually know what the metric space is. We know there's some metric space, and we assume that people's rankings are consistent with this metric space. Does this make sense? Okay? So it's a very weak assumption. I'm not assuming they're on a line or on a 2D grid or a 3D grid or anything. Okay? And then I'm going to assume that the distortion of a candidate J is, I'm going to say max, even though I should say soup, I'm going to say max. I'm not going to explain why I'm saying max as opposed to soup. Okay? So please excuse me for this one. Is the max over all metric spaces D consistent with sigma? Okay. So because we are given these rankings, not every metric space could potentially be consistent with these rankings. Does that make sense? So for example, if let's say this is sigma 1 and sigma 1 is A, B, and C, then it cannot happen that this is 1 in the metric space, this is C, this is B, this is A. That's not possible, right? Because one ranked A above B above C. Okay? Right. So this metric space cannot be consistent with, assuming this is a line, cannot be consistent with the ranking A, B, C. So you can take a max over all metric spaces which are consistent with this ranking of the sum over all the voters of Dij, okay, divided by the min over all j star of the sum over all I of d of I comma j star. Okay. Now I know this definition is a handful, and it'll take a minute to parse. So let's just parse it. So what this max is saying is that we're going to look at the worst possible metric. Given any j, we're going to find the metric which makes j look the worst possible. Okay, and worst possible in what way? Worst possible in terms of how bad J is, was the penalty. Every voter wants someone close to them in the metric space, right? They want someone who's far from them in the open space. So this is the penalty for J. How far was the total distance from J to everybody else? This is the penalty of the best possible candidate that you could have picked. The best possible candidate, this is typically called the median. So in a general metric space, the notion of a median is the one that minimizes the sum of the distances to everybody. So this is the median. This is the median candidate in terms of the distances of the voters in this metric space D. This is the penalty for J. We take the ratio and we find the worst metric, and that's the distortion of J. Does this make sense? Okay. So let's take an example. So let's say our metric space, let's say we have a ranking ABC Let's say we just have a ranking, we have just two people. We have a ranking AB and a ranking BA. Okay. Does this make sense? So we have exactly two candidates. Their rankings are AB and BA. Okay. Can someone suggest which candidate we should pick as the winner? Okay. And without loss of generality, we could pick one. Just by symmetry, you can say they're both going to have the same distortion. Okay. So let's pick A. Okay, so let's pick A as the winner. Okay. Can the distortion be arbitrary? Could it be that A is very, very, very far away from sigma 2, but A and B are right very close to sigma 1, and so the distortion could be very large? Okay. So let's see how large the distortion could be. Okay. So first of all, the distance of A from sigma 1 cannot be larger than the distance of B from sigma 1, right, because of the ranking constraints. So any large distortion that comes is not going to come, we picked A, any large distortion that comes is not going to come from sigma 1. Okay. Let's think of sigma 2. D of 1 comma A is less than or equal to D of 1 comma B. D of 2 comma B is less than or equal to D of 2 comma A. And they are required to be metrics. Okay. So these are not arbitrary distances. If these are arbitrary distances or arbitrary values, then I could have set D of 1 comma A equal to 1, D of 1 comma B equal to 1, D of 2 comma B equal to 0, D of 2 comma A equal to 100, and I would have had a huge distortion. Right? Does that make sense? I can't quite do it. Why can't I do it? Because of the metric constraint. Because of the metric constraint, the distance between 2 and A cannot be larger than the distance between 2 and B, plus the distance between B and 1, plus the distance between 1 and A. Does that make sense? By triangular inequality, right? Or in this particular case, quadrilateral inequality. So distance between 2 and A cannot be larger than the distance between 2 and B, between B and 1 and A. Okay? Now the distance between 1 and A is something that any algorithm has to pay. Any J star has to pay because A is before B in the ranking. Okay? Whether you pick B as the winner or A as the winner, the distance from 1 cannot be more than 1 comma A. Okay? So you can charge this to the algorithm. The distance between B and 1, you can't quite charge to the algorithm if J star ends up being A, but if J star ends up being B, then you can also charge this to the algorithm. And 2 comma B also you can charge to the algorithm if the algorithm ends up picking B. Does it make sense? And so you can basically, this quadrilateral inequality will immediately prove that in this particular case, the distortion of A cannot be more than 3. By symmetry, the distortion of B also cannot be more than 3. Okay. Does that make sense? Okay. So, what should I say? So in fact, in this particular case, this is sort of like this is almost like a formal proof, right? The distance cannot be more than 3. You can actually have distortion 3. So without loss of generality, let's say we picked 1. So does it make sense how you could have, again, without seeing a formal proof, is it clear that how I could have argued in this case that distortion cannot be more than 3? Okay. So we picked A. Okay. So because we picked A, the distance that we ended up paying was D of 1 comma A. Yeah. So the numerator can be at most D of 1 comma A plus D of 1 comma B. That's exactly the numerator. Okay. The denominator, no, sorry, the numerator is 1 comma A and 2 comma A. That's the numerator because I picked A as the winner. The denominator could be either D of 1 comma A plus D of 2 comma A, in which case it's just 1, or it could be D of 2 comma B plus 1 comma B. Right? Now, because of my ranking constraint, D of 1 comma A is less than or equal to D of 1 comma B, right? Because A is before B in the ranking for sigma 1, So I'm not particularly concerned about this pair. I have to really focus on how much worse how bad could D of 2 comma A be. So d of 2 comma a is less than equal to d of 2 comma b plus d of 1 comma b plus d of 1 comma a. Okay. So this is just the denominator, right? This is also just the denominator, because d of 1 comma a is less than equal to d of 1 comma b, and this d of 1 comma a is also just the denominator, right? Is that clear? So this is at most the denominator, this is at most the denominator, and this is also at most the denominator. Therefore, the thing at the top could be at most thrice the denominator, okay? And hence you could be at most a factor of 3 of. Okay? Now, the nice thing to remember here is that the only things we used were these triangle inequalities, and these triangle inequalities sort of sum. Okay? So the only thing we used here was that A also 1 as often as B 1. A 1 against B as often as B 1 against A. Does it make sense? And so, can someone guess what I'm going to say, what I may say next? So, is the argument for 3 clear now? And so, I'm not going to formally prove the next 2 statements I'm going to make, but just informally, is it clear that the main argument here is that this, I could have had, instead of having 1 voter, I could have had many, many voters. I could have had like sigma 3, which looks like sigma 1, then sigma 4, which looks like sigma 2, then sigma 5, which looks like sigma 1, sigma 6, which looks like sigma 4, and so on, right? And as long as I'm comparing A and B, and notice here I'm only comparing A and B, it won't really matter that I had many, many, many copies of these. The same argument would basically apply, right? And so hence, if A is a Condorcet winner, it could have distortion at most 3. Does it make sense? And that's a very strong result. I mean, it might sound like, of course, in this community, a constant factor of 3 may not sound that exciting. But in the approximation algorithms of the CS theory community, a constant factor of 3 sounds very exciting. And so a factor of 3, so what I just proved somewhat informally and via a picture, admittedly not formally, is that if A is the Condorcet winner, then the distortion of A can be at most 3. Okay? And that tells you that being a Condorcet winner is actually something, is something concrete, because we started with a very general description of sort of these metric spaces. So, and this is the worst possible metric space. So if you have a Condorcet winner, you'll never be able to find any underlying metric space. You'll never be able to demonstrate to me any preferences. It sort of makes sense as a metric space, under which this would be more than a factor 3 worse than the optimum. So the Condorcet can't be too bad under any situation. Yes? Yeah, so no matter, so if you pick the Condorcet winner, then no matter what the underlying public opinion is, like given a ranking, you have no idea what underlying space that ranking is coming from. No matter what the underlying opinion space is where people's rankings are drawn from, you're not going to have a distortion of more than 3. The winner is going to be at least acceptable up to 3. No, not for everybody, in aggregate, because this is to society. So just like I said, last time I had a notion of social welfare, you could think of this as a notion of social cost. Okay? And so the social cost of the Condorcet winner is no more than a factor of 3 compared to the optimum. Okay? And of course, you would like to get optimum, but it's at least 3, it's not infinite. Okay? It's always possible that you can find a metric space consistent with any ranking. It's not obvious, but it's true. And the way you could do it is you could sort of put all the candidates right almost at the same point, and you could just like vary one dimension. You could have like a separate dimension for each, pretty much a separate dimension for each voter. So in fact, they could also be in a geometric space. Yeah, it's not obvious, but it's true. It's obvious with half an hour of thinking. It's not obvious without half an hour of thinking, but it's true. There's always a metric space which is consistent with the ranking. Okay. And the Condorcet winner has distortion at most 3. The Copeland winner has distortion at most 5. The 5 proof is very long, but I'll give you a 9 proof. Okay. So, by the way, let me at least write this down. Okay. If J is the Condorcet winner, distortion of J is at most 3. Okay. All the rules that we talked about before, which were not Condorcet rules, plurality, single transferable vote, and Borda, they can all have distortions going to n. Okay. So this is an actual, this is a substantial, no, sorry, it's not single transferable vote. Single transferable vote is distortion of log n. But it goes to infinity. Sorry, it doesn't go to n, but everything else has distortion. All these non-Condorcet voting rules that we discussed. This is not a theorem about all non-Condorcet rules. There might be some other non-Condorcet rule which is good. But plurality, Borda, and single transferable vote all have distortions that go to infinity as n goes to infinity, as the number of voters goes to infinity. Okay? Whereas if there's a Condorcet winner, then the distortion of J is less than or equal to 3. This might look like a funny theorem because I'm saying like if pigs could fly, then horses would whistle or something, right? Because it's a Condorcet winner which may not exist. Okay? But there's a very beautiful property of a Copeland winner which immediately gives you 9 for Copeland. Yes?
For plurality and Borda, can we show lower bound which goes to infinity?
Yes. The question is for plurality and Borda, can we show a lower bound? Yes. We can show a lower bound for plurality and Borda which goes to 3. We can also show a lower bound for the Condorcet winner case which goes to infinity. The same example that I showed you, that exact example is also a lower bound proof saying that even if you have a Condorcet winner, you can have a distortion of 3. So for Condorcet winners, the distortion of 3 is tight. There's nothing which can ever achieve distortion of more than 3, even if even the Condorcet winner can have a distortion of 3. Yeah. So what about Copeland? Well, Copeland has 5, distortion of 5, and I'm going to give you a very quick proof of 9. Okay? Again, maybe not a complete proof, but like enough of a proof that if you wanted, you could reconstruct the full proof in proof of 9 in like 5-10 minutes yourself. Okay? If A is a Copeland winner, okay. By the way, this result is due to Anshelevich et al. So the model that I'm describing is not, this whole framework of distortion, metric distortion didn't come from me. It's from this guy, Elliot Anshelevich, and his research group in RPI. And I'd been struggling with these problems for a long time. And as soon as I saw this, it was like a eureka moment, saying this is just the right way to think about winners. So pretty much all the results that I'm describing are from his paper, not something that we proved. Okay. If A is the Copeland winner, then for all C, there exists B, for all C, either A beats C in a pairwise election. And by the argument that we just had, that means that if you put A in the numerator and C in the denominator, the distortion would be at most 3. Or there exists B such that A beats B and B beats C in a pairwise election, okay? Which means the distortion would be at most 9. Because if you put A in the numerator, B in the denominator, you would get 3. If you put B in the numerator, C in the denominator, you would get 3, which means for A and C, the distortion would be 9. And so this proves that the Copeland winner has a distortion of at most 9. Whereas all those other rules, plurality, single transferable vote, and Borda have distortion that goes to infinite. Okay. 5 is known. 3, there's a conjecture which says that there exists some rule which achieves a distortion of 3. Okay. And it's, in my mind, it's like one of the biggest open problems. I mean, not everyone in social choice might agree, but in my mind, it's one of the most beautiful open problems in social choice, which is, can you devise a rule, a deterministic rule, which is a distortion of 3, or prove that no rule can have a distortion of more than 5, or of less than 5. Okay. So is it clear? So Copeland is 3. Sorry, Copeland is 5. Okay, it's known to be 5. There's an example which achieves 5. Okay. Rank pair is greater than or equal to 5. Copeland is 5 because we have an upper bound of 5 and a lower bound of 5. Rank pair we know is at least 5. We don't know what the upper bound is. And the question is, what's the best rule? And nobody knows. And so if you can get it down to 3, it'll be great. It's a useful framework because it's a very quantitative answer of which voting rule is better. It's also a very quantitative reason for favoring condorcet winners, because condorcet winners have a distortion of 3. Okay? So I'm going to stop here. I'm a little bit over time. And as a result, I'm not going to be able to do something in the next lecture, but I think this was maybe more interesting.